This is your video for 6.2 definite integrals, and this will also be split into two videos, so this is your part one. The first thing we have on here is just something about sigma notation, and you should recall from Algebra 2 that sigma notation, that's something that enables us to express large sums in compact form. So rather than having to write out all of those terms separately, we can do a sigma. That's that capital Greek letter that kind of looks like a weird E, and that expresses how many terms we have. So your A sub k would be your term or like your equation. You start with whatever number's on the bottom, and then you go to the number that's on the top using integers. So this one would start at A sub 1 and then go the whole way up to A sub n. So sigma itself does mean sum. Your index k, again, is going to tell you where to begin, and then the number above is going to tell you where to end. There is a breakdown on page 282 in your textbook of the partitions and the subintervals. And I actually wrote out a sigma here. If we have the sigma from n equals 1, I use n instead of k, but it doesn't really matter what letter you use there as long as it's consistent. So from n equals 1 to 5 of the equation n cubed, that would be 5 terms being added together, 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed. So you plug in the 1, then the next integer, then the next integer, until you get the whole way up to 5, which is on the top. So with the partitions and the subintervals, your sum, your S sub n that we have listed here, that's going to depend on the partition P, so basically how you're splitting it up, and your choice of numbers C sub k, so that's going to be the numbers that you're plugging in there. This is a way to express a Riemann sum for f on some interval. So this is just really a mathematical way to express what we've been doing with the Riemann sums. Your Riemann sums are all going to converge to a common value as long as your length of the subinterval tends to 0. So remember before we did a couple of examples where the width was 1, we did a couple where the width was a fourth, sometimes the width is a half. So as that width of your interval gets smaller and smaller and smaller and tends to 0, that's when your n is going to get really, really huge because you're making a huge number of slices. All of the Riemanns are going to converge to some type of common value. And that common value is actually going to be the definite integral. So this is theorem 1. All continuous functions are integrable. If it's continuous, you can integrate it. So the definite integral has to exist. So we have here our limit as n approaches infinity from k equals 1 to n. So again, you're doing an infinite number of slices, and C sub k is arbitrarily in some kth interval. We aren't really going to be doing a whole lot with this type of notation. We are going to be switching it into integral notation, which you'll see here in a bit. In your textbook, there's also a terminology and notation section on page 283 to 284. This kind of goes through some of the origins of where some of these terms and letters came from. So first of all, originally, whenever calculus was first being discovered, the Greek notation, they used delta. So then again, that's where the sigma came from as well, because sigma is a Greek letter. Your limit as delta x approaches 0, so that would be like the limit as h approaches 0 whenever we looked at the original definition of derivative. Delta y over delta x, we eventually, for the Roman notation, turned that into dy dx, which, you know, delta begins with the letter d, so that's where that came from. Then we have the limit as n approaches infinity of the sigma, so that's what was just on the previous page, times the delta x. That is equal to the integral from a to b of our function f of x and then dx, so integrating with respect to x. So the Roman notation, this one up here, this dy dx, and the integral from a to b of f of x dx, those are going to be the notations that you commonly see and you will use in the calculus that we do in this class. So here's some important things about the integral. This was the same integral that was on the previous page. The a at the bottom is what we consider the lower limit of integration. So that's going to be where you're starting. The b is the upper limit, and then that stretched out s-looking thing, that is the integral sign. The function is what we call the integrand, so that's what you're actually going to be finding the antiderivative of, and then the d, whatever variable is there, that is the variable of integration. So with this particular setup, we would be integrating with respect to x. So this would, if you were stating this, this would be the integral of f from a to b. You always start at the bottom and end at the top. Now, you can change up the variable that's in the function. That's what the two things at the bottom are. So if you have an f of t function, that would be a dt, or an f of u function, that would be a du. So you do need to make sure that whatever variable is after the d, that matches the variable that's in the problem. And this is something that's going to come up in chapter 7, whenever we look at 7.2, integrating using u substitution, because in those cases, you may have to change your variable of integration so that it matches whatever variable you have in your function. Now, up here again, since it doesn't matter what letter we use to run from a to b, the variable of integration, sometimes called a dummy variable, it is important that it matches, but we're really not going to do anything else with it aside from just making sure that it matches. So with this first example, we're given the integral from -1 to 3 is partitioned into n subintervals of equal length. Let m sub k denote the midpoint of the k subinterval, express the limit below as an integral. So you're basically just taking what's here and you're expressing it as an integral. They do give me this -1 and this 3 up here. Those are going to be my limits of integration. I'm actually sitting at my computer right now. I'm not standing at the smartboard, so this may look a little bit messy because I have to use my mouse to draw this. So there's my integral. I'm going from -1 to 3, so I'm going to put my -1 at the bottom, my 3 at the top, and basically all of these mk's, m sub k's, those are going to be your variable. So my equation is going to be 3x squared minus 2x plus 5, and the variable of integration is x, so I'm going to put a dx on the bottom. And that's all you have to do. That's all you have to do to write this in expressing this as an integral. It is important that you do find what the interval is, because there's nowhere in this summation that it actually tells you that your interval is from -1 to 3. So that is something you'll have to get from up in the directions. So that brings us to another definition. You notice there's a lot of setup in this section, and this is mainly because this is really getting us into some of the setup with the integral. So really setting up what the integral means, why is it important. So if y equals f of x is non-negative and integrable over a closed interval a to b, then the area under the curve y equals f of x from a to b is the integral of f from a to b. So the whole reason why we do definite integrals is to find the area under the curve. And you can see down below, we can use integrals to calculate area, and we can use areas to calculate integrals. So they go both ways. If you have an integral, then you know what the area is. If you know what the area is, you know what the integral is. It's very, very useful to have that available to us. This is where I'm going to stop the first video. The second video is going to have a lot of examples and ways to calculate the definite integral. Again, this whole chapter is pretty much based around area under the curve and looking at the definite integral. So you're going to get a whole lot more from here on about integrals and what they mean. So go back and rewatch this video. This is really a basic introduction to the importance of the integral. And contact me if you have any questions.